Space, the final frontier. A cathedral of silence so vast and so ancient that the very light reaching our eyes tonight departed its source before our planet even existed. We look up and we look back. Every glance at the night sky is an act of archaeology, a window not into the present, but into the deep and staggering past. And yet, for all our instruments, all our mathematics, all the centuries of accumulated wonder and rigorous inquiry, the universe guards its most fundamental secrets with extraordinary tenacity. The black hole. Perhaps nothing in the known cosmos has seized the human imagination more completely. Perhaps nothing has resisted our understanding more stubbornly. Tonight, we journey to the edge of what is knowable. We will descend, conceptually at least, into the hearts of the most extreme objects in existence. We will ask what happens to space, to time, and to matter itself when gravity becomes so overwhelming that not even light can outrun it. We will trace the arc of a black hole's life, from its violent birth in stellar catastrophe to its near-eternal reign as one of the last surviving structures in a dying universe. And along the way, we will discover something unexpected, that black holes, for all their reputation as the ultimate destroyers, may also be among the universe's most creative forces, that at the intersection of destruction and creation lies the deepest mystery of all, the architecture of extremity. To understand a black hole, we must first understand what it takes to break the universe. Gravity is, in a sense, the most familiar force we know. It keeps our feet on the ground. It holds the moon in its steady circuit. It binds the earth to the sun, and the sun to the slow, graceful rotation of our galaxy. But gravity is also, in a fundamental sense, the weakest of nature's fundamental forces. A child can pick up a paperclip with a small magnet, defeating the gravitational pull of an entire planet with nothing more than a toy. And yet, given sufficient mass, given sufficient concentration, gravity reveals a character that dwarfs every other force in nature. It is not the strength of gravity that makes black holes possible. It is gravity's patience, its inexhaustibility, its refusal to ever fully turn off. Every object with mass distorts the fabric of space-time around it. This is the central insight of Einstein's general theory of relativity, published in 1915, though the concept was so radical, so geometrically alien, that even Einstein himself struggled to accept some of its consequences. The Earth distorts space-time, causing the Moon to follow a curved path that we experience as an orbit. The Sun distorts space-time more dramatically, bending even the trajectories of light passing near its surface, an effect observed and confirmed during the solar eclipse of 1919, catapulting Einstein to worldwide fame almost overnight. But what happens when mass is compressed into a sufficiently small volume? What happens when the distortion of space-time becomes so severe, so acute, that not even the fastest thing in the universe can escape? The answer is a singularity, a point, or more precisely, a region, where our familiar laws of physics cease to function in any meaningful way, where density becomes, in the language of mathematics, infinite, where space-time curvature approaches values that shatter our models. Around this singularity lies the event horizon, an invisible boundary in space that serves as a one-way membrane. Cross it, and no information, no matter, no signal of any kind can ever return. The black hole does not pull in the conventional sense. It is not a cosmic vacuum cleaner, roaming the universe and sucking up everything around it. Rather, the geometry of space-time itself has been so thoroughly warped that every possible path forward, every direction a particle or photon could conceivably travel, curves inward. There is no route out. The very concept of escape becomes geometrically meaningless. This is what makes a black hole not merely powerful, but philosophically disorienting. It is not an object in space. It is a region of space that has been restructured so completely that our ordinary intuitions about movement, direction, and time no longer apply. The birth of darkness. Black holes do not simply materialize from nothing. They are born, and their births are among the most spectacular and violent events the universe has to offer. The story begins, as so many cosmic stories do, with a star. For most of its life, a star is a masterpiece of balance. At its core, nuclear fusion converts hydrogen into helium, releasing enormous quantities of energy in the process. This energy presses outward against the star's own gravity, which presses relentlessly inward. The result is a kind of dynamic equilibrium, a constant negotiation between two titanic forces, sustained for millions or billions of years, depending on the star's mass. But this equilibrium is not permanent. It cannot be. Every star, however massive, however brilliant, carries within itself a finite supply of fuel. And when that fuel is exhausted, the negotiation ends. Gravity, which has been biding its time for millions of years, finally wins. What happens next depends critically on the mass of the star. A star like our own Sun will, in approximately 5 billion years, exhaust its hydrogen supply and expand enormously into a red giant before shedding its outer layers in a gentle, glowing cloud of gas and dust called a planetary nebula. What remains at the center will be a white dwarf, a dense, hot, slowly cooling ember of carbon and oxygen, roughly the size of the Earth, held up not by nuclear fusion, but by the quantum mechanical pressure of tightly packed electrons. But for stars with significantly greater mass, the fate is far more dramatic. When a star roughly 8 to 20 times the mass of our Sun exhausts its fuel, the core collapse happens with catastrophic speed. In less than a second, less than the time it takes to blink, the core implodes from something the size of the Earth to something barely 20 kilometers across. The infalling outer layers, which have been drawn toward the core by gravity, slam into this newly formed ultra-dense object and rebound outward in an explosion of almost incomprehensible energy. This is a supernova. For days or weeks, a single exploding star outshines entire galaxies containing hundreds of billions of stars. The energy released in a single supernova explosion exceeds what our Sun will produce across its entire 10 billion-year lifespan by a factor of tens of thousands. What remains at the center after the outer layers have been blasted into space is a neutron star. A neutron star is, in many ways, as extraordinary as a black hole. It packs roughly 1.5 times the mass of our Sun into a sphere barely 20 kilometers in diameter. A teaspoonful of neutron star material, were it somehow transported to Earth, would weigh several 100 million tons. Some neutron stars rotate hundreds of times per second, sweeping beams of radio waves across the cosmos like cosmic lighthouses. We call these pulsars. But even neutron stars have their limits. For stars above a certain mass threshold, roughly 20 to 25 solar masses, even the quantum pressure of neutrons cannot halt the inward collapse. The core continues to compress, passes through the neutron star stage, and keeps collapsing. Collapses past all known forms of matter, all the way into singularity. A stellar mass black hole is born. The universe has, in a span of milliseconds, created a region of spacetime so distorted that the known laws of physics simply do not apply within it. The mathematics of general relativity, which describes the birth and behavior of black holes with extraordinary precision everywhere else, breaks down at the singularity itself. It is not that we lack sufficiently powerful computers or sufficiently detailed observations. It is that the equations, faithfully solved, return values of infinity. And infinity, in physics, is almost always a sign that something fundamental is missing from our understanding. Varieties of the void. Not all black holes are created equal. The universe, in its characteristic fashion, has produced black holes across an extraordinary range of scales and characters. Stellar mass black holes, the kind born from collapsing stars, typically range from about 3 to perhaps 100 times the mass of our Sun. Thousands of them almost certainly populate the Milky Way, though their very nature makes direct detection difficult. We find them most readily when they exist in binary systems with companion stars. Material drawn from the companion forms an accretion disk around the black hole, swirling inward with tremendous speed and heating to temperatures of millions of degrees. This ultra-hot gas radiates powerfully in X-rays, and it is these X-ray emissions that betray the black hole's presence to our telescopes. But at the other end of the scale, something far more extraordinary exists. At the center of nearly every large galaxy in the observable universe, including our own, sits a supermassive black hole. Not 10 times the mass of our Sun, not 100 times, not even 1,000,000 times. Supermassive black holes range from roughly 1,000,000 to many billions of solar masses, and they represent some of the most extreme objects the universe has managed to produce. The one at the center of our own Milky Way, known as Sagittarius A star, has a mass approximately 4 million times that of our Sun. For decades, astronomers could only infer its presence from the behavior of nearby stars, which orbit an invisible central point with speeds and trajectories that can only be explained by an enormous concentration of mass. But in 2019, and again in 2022, humanity achieved something that would have seemed like pure fantasy a generation earlier. The Event Horizon Telescope, a planet-spanning network of radio observatories working in concert, produced the first actual images of black hole event horizons. First, the supermassive black hole at the heart of the galaxy Messier 87, over 50 million light-years away, and then Sagittarius A star itself. Glowing rings of superheated gas, circular shadows at their centers, exactly as Einstein's equations had predicted over a century earlier. How supermassive black holes came to exist at all remains one of the great open questions of modern cosmology. The universe is only 13.8 billion years old. Yet astronomers have found supermassive black holes with masses of several billion suns existing when the universe was less than 1 billion years old. The stellar mass black hole pathway simply cannot account for this. There was not enough time. Something else must have happened. Perhaps the direct collapse of enormous gas clouds in the early universe. Perhaps the rapid merging of many intermediate mass objects. Perhaps something we have not yet conceived. The origin of supermassive black holes remains one of the deepest mysteries in astrophysics. And then there are intermediate mass black holes, the missing middle tier between stellar mass and supermassive. They are predicted to exist. There is suggestive observational evidence, but they are frustratingly difficult to pin down, lurking in the dense stellar environments of globular clusters and the central regions of smaller galaxies, neither as numerous as stellar mass black holes, nor as obviously luminous as their supermassive cousins. Finally, theorists have long speculated about the possible existence of primordial black holes, formed not from collapsing stars, but from the extreme density fluctuations of the universe's earliest moments. If they exist, primordial black holes could range in mass from the equivalent of a small asteroid to far larger values. Some researchers have suggested they might account for a fraction of the mysterious dark matter that makes up roughly 27% of the universe's total energy content. Direct observational evidence remains elusive, but the search continues with growing sophistication. The event horizon and the theater of extremity. The event horizon is not a physical surface. There is no wall there, no barrier you could touch or see. A traveler falling toward a black hole would not experience any dramatic sensation as they crossed it. No alarm would sound. No light would flash. From the perspective of the infalling traveler, nothing locally unusual would happen at the moment of crossing. And yet, the event horizon represents perhaps the most absolute boundary in nature. On one side, information can propagate freely throughout the universe. On the other side, nothing, not matter, not energy, not even a single photon carrying the smallest fragment of information, can ever return. The event horizon is the universe's strictest one-way door. For a distant observer watching someone fall toward a black hole, something remarkable and deeply strange would appear to happen, because extreme gravity warps time as well as space, a consequence of general relativity confirmed with extraordinary precision by GPS satellites, which must correct for the fact that time runs measurably faster at their altitude than at Earth's surface. The infalling traveler appears to slow down. The images of the traveler become increasingly redshifted as their light climbs out of the deepening gravitational well. As the traveler approaches the event horizon, they appear, from outside, to slow to a halt, their image growing dimmer and redder until they fade from view altogether. An outside observer never actually sees them cross the horizon. To the outside universe, they are frozen there, asymptotically approaching, but never quite arriving. From the traveler's own perspective, of course, something very different is happening. Depending on the size of the black hole, tidal forces, the difference in gravitational pull between the head and feet, may or may not be immediately significant. For a stellar mass black hole, these tidal forces near the event horizon would be so extreme that a human body would be stretched vertically and compressed horizontally in a process physicists have, with characteristic understatement, termed spaghettification. But for a supermassive black hole, the horizon lies so far from the central singularity that tidal forces there might be relatively gentle. A traveler could cross the event horizon of a billion solar mass black hole without feeling anything unusual in that instant. But the destination is not in doubt. Once inside, every possible trajectory leads toward the singularity. The future, quite literally, is at the center. There is no choice of direction that does not ultimately arrive there. Around and outside the event horizon, the environment of an actively feeding black hole is anything but quiet. When material falls toward a black hole, whether gas stripped from a companion star, debris from disrupted stars that wandered too close, or intergalactic gas drawn in over cosmic timescales, it does not fall straight in. It carries angular momentum. It spirals. It flattens into a disk. And as material in the disk collides, compresses, and heats through friction and magnetic turbulence, it releases enormous quantities of energy before crossing the point of no return. This is the accretion disk, and it is among the most luminous structures in the universe. The accretion disks around active supermassive black holes, known as quasars or active galactic nuclei depending on their orientation and properties, can outshine their entire host galaxy by factors of hundreds or even thousands. A single quasar powered by a black hole consuming material at a prodigious rate can radiate more energy than 1 trillion suns. And, in many systems, not all of the infalling material actually falls in. Powerful magnetic fields threading through the accretion disk can funnel some material into relativistic jets, columns of plasma accelerated to nearly the speed of light and launched perpendicular to the disk plane. These jets can extend for millions of light years, carrying extraordinary amounts of energy far out into the surrounding galaxy and beyond. The jet of the galaxy Messier 87, the same black hole whose image was captured by the Event Horizon Telescope, extends some 5,000 light-years from the central black hole. It is one of the most powerful structures in the known universe. Hawking's revelation. The black hole is not forever. For most of the 20th century, black holes were understood to be permanent. Once formed, they grew. They could merge with other black holes when their host galaxies collided. They could consume vast quantities of matter and energy. But they were, as far as classical physics was concerned, immortal. Then, in 1974, a young British physicist named Stephen Hawking made one of the most surprising theoretical discoveries in the history of science. By applying the principles of quantum mechanics to the region just outside a black hole's event horizon, Hawking demonstrated that black holes must radiate. Slowly, imperceptibly by any current technology, but continuously and inevitably. The mechanism is subtle and beautiful. Quantum mechanics tells us that the vacuum of space is not truly empty. At scales far smaller than an atom, space is a seething froth of quantum activity. Pairs of virtual particles, a particle and its corresponding antiparticle, are constantly flickering into brief existence and then annihilating each other, borrowing energy from the vacuum for the tiniest fraction of an instant before repaying it. Normally, this is a zero-sum process. Particles form, annihilate, and the vacuum is unchanged. But at the event horizon of a black hole, something different can happen. One member of a virtual pair can find itself just inside the horizon, while the other remains just outside. They can no longer annihilate. The one that fell inside is effectively consumed by the black hole. The one outside escapes into space as real radiation. The energy for this radiation has to come from somewhere, and it comes, remarkably, from the black hole itself. The black hole loses a tiny amount of mass with every particle that escapes. For large black holes, this process is extraordinarily slow. A black hole of a few solar masses would radiate at a temperature barely above absolute zero, a temperature so cold that it would be completely undetectable against the background warmth of the cosmic microwave background radiation. It would take an almost incomprehensibly long time to evaporate, far longer than the current age of the universe. But the process accelerates as the black hole loses mass. As mass decreases, temperature increases. As temperature increases, radiation intensifies. Mass decreases faster. Temperature increases further. The process is self-reinforcing. And at the very end, in what Hawking predicted would be a final burst of energy, the last vestiges of the black hole would vanish in a flash of high-energy radiation. This prediction, Hawking radiation, has never been directly observed. The temperatures involved for any known black hole are so extraordinarily low that detection is, for now, beyond any conceivable technology. but the theoretical derivation is compelling and has withstood decades of scrutiny from physicists who have approached it from many different angles, using many different mathematical frameworks. Almost all of them arrive at the same conclusion. Hawking was right. But Hawking's discovery opened up what may be the deepest paradox in all of modern physics. If a black hole eventually evaporates completely, and the radiation it emits in doing so is, as Hawking's original calculation suggested, purely thermal and random, carrying no information about what fell in, then what happened to all the information encoded in the matter that formed the black hole and everything it subsequently swallowed? In quantum mechanics, information is sacred. The laws of physics are fundamentally reversible. If you know the exact state of a physical system at one moment, you can, in principle, reconstruct its entire past and predict its entire future. Information is never truly destroyed. But if a black hole swallows a star, burns for trillions of years, and then evaporates into featureless thermal radiation, the information about that star appears to be gone forever. This is the black hole information paradox. It has occupied some of the finest minds in theoretical physics for over 50 years. It sits at the intersection of quantum mechanics and general relativity, the two great pillars of modern physics that, despite their extraordinary individual success, remain fundamentally incompatible with each other. Resolving the information paradox may require a complete theory of quantum gravity, a framework that does not yet exist and that represents perhaps the greatest outstanding challenge in fundamental physics. Some physicists believe information escapes gradually, encoded in subtle correlations within Hawking radiation that only reveal themselves when the black hole has nearly finished evaporating. Others have proposed radical ideas involving firewalls at the event horizon, or the idea that the interior of a black hole might be connected through a quantum wormhole to distant regions of spacetime. Still others have suggested that a small remnant might survive the evaporation process, carrying all the information within it forever. Each proposed solution brings its own set of deep puzzles. The information paradox has proven to be not a single problem, but a doorway, leading to increasingly fundamental questions about the nature of spacetime, the nature of information, and, ultimately, the nature of reality itself. Spaghetti, fire, and the tidal frontier. There is a thought experiment that physicists have been fond of since the early days of black hole theory. Imagine you are falling into a black hole feet first. What do you feel? The answer, it turns out, depends enormously on the size of the black hole in question. And the physics behind that dependency reveals something genuinely important about the nature of these objects. Tidal forces are, in their everyday form, the reason the moon raises tides on Earth. The side of our planet facing the moon is slightly closer to it, and therefore feels a slightly stronger gravitational pull than the side facing away. This differential pull stretches the Earth very slightly in the direction of the moon, producing the tidal bulge that our oceans follow as the Earth rotates beneath them. Now, scale this up. As you fall toward a stellar mass black hole, a relatively small object with perhaps 10 times the sun's mass crushed into a sphere perhaps 30 kilometers across, the difference in gravitational pull between your head and your feet becomes extraordinary. The closer you get, the steeper the gradient becomes. Your body is stretched in the direction of the black hole's center and simultaneously compressed from the sides, squeezed like a tube of toothpaste. This process, again, is what physicists call spaghettification, and it is as unpleasant as it sounds. For a stellar mass black hole, this process would begin well outside the event horizon and would be rapidly fatal. But for a supermassive black hole, say one of several billion solar masses, the event horizon lies so far from the central singularity that the tidal gradient at that distance is actually quite gentle. The horizon of such a black hole might have a radius of several billion kilometers, comparable to the distance between the Sun and the outer planets of our solar system. At those distances, the difference in gravitational pull across a human body, or even across a spacecraft, would be relatively modest. An observer could cross the event horizon of such an object without experiencing anything immediately dramatic. The horror, in that case, would come later. As the infalling observer moved deeper into the black hole, toward the singularity, tidal forces would intensify without limit. The singularity is not a gentle end point, but the crossing of the horizon itself would be, for a sufficiently massive black hole, deceptively serene. This thought experiment captures something important about the event horizon. It is not a physical structure. There is nothing there, no wall, no surface, no flash of light marking the boundary. The horizon is a feature of space-time geometry, a surface defined by the behavior of light, not by any physical substance. And this makes it deeply different from any other boundary we encounter in ordinary experience. Near the event horizon, but outside it, physics becomes spectacular. In the region known as the ergosphere that surrounds rotating black holes, and essentially all astrophysical black holes rotate, having inherited the angular momentum of the material from which they formed or subsequently consumed, a fascinating effect occurs. The rotation of the black hole drags space-time itself around with it, a phenomenon called frame dragging, or the lens-Thirring effect. Space itself is pulled into rotation by the spinning black hole, just as a spinning drill bit might drag the material around it. In the ergosphere, no object can remain stationary relative to the distant stars. Space-time is dragged forward with such relentless force that standing still requires moving faster than light in the backward direction, which is impossible. Every object in the ergosphere, every particle of matter, every photon, is compelled to co-rotate with the black hole. But the ergosphere lies outside the event horizon. This means that, in principle, energy can be extracted from it. A process described by physicist Roger Penrose in 1969, appropriately called the Penrose process, allows a hypothetical visitor to the ergosphere to gain energy from the rotation of the black hole itself by splitting a particle into two parts, allowing one to fall inward while the other escapes with more energy than the original particle brought in. The difference is paid for by a tiny reduction in the black hole's rotational energy. Whether this process happens naturally in astrophysical settings, perhaps powering some of the jets we observe shooting from actively feeding black holes, is a subject of active research. The Blandford-Znajek mechanism, proposed in 1977, suggests that magnetic fields threading through a rotating black hole's ergosphere can extract rotational energy and channel it into the relativistic jets seen in quasars and active galactic nuclei. Some of the most powerful jets ever observed may be running, at least in part, on stolen spin. A black hole's rotational energy is not small. For a maximally spinning black hole, roughly 29% of its total mass energy is stored in its rotation. That is a staggering energy reservoir, and the universe appears, in at least some settings, to have found a way to tap it. The complexity of behavior near a black hole's event horizon, tidal forces, frame dragging, ergospheres, Penrose processes, jet formation, speaks to a broader truth. Black holes are not simply holes. They are extraordinarily rich physical environments, governed by a subtle interplay of general relativity, electromagnetism, and quantum mechanics. They are not the universe's trash bins. They are among its most complex and dynamic structures, black holes and the architecture of galaxies. For most of the 20th century, black holes were understood primarily as curiosities, exotic endpoints of stellar evolution, fascinating theoretically, but isolated, and essentially passive objects that had little to do with the large-scale structure of the universe. That picture has been overturned completely. We now know that supermassive black holes and their host galaxies are intimately connected, co-evolved, bound together in a relationship of mutual influence and mutual shaping that has played out over cosmic timescales. The mass of a supermassive black hole correlates tightly with properties of the surrounding galaxy, particularly the mass and velocity dispersion of the central bulge of stars. This is a strange and striking fact. The event horizon of even a supermassive black hole is tiny compared to the galaxy around it. Sagittarius A star's event horizon would fit comfortably inside the orbit of Mercury around our Sun. Yet somehow, this tiny object and the billion light-year scale galaxy around it have grown together in proportion. The likely explanation involves feedback. When a supermassive black hole is actively feeding, when it is accreting large amounts of material and shining as a quasar, the energy and radiation it releases are not simply lost. They heat the surrounding gas. They drive powerful winds outward through the galaxy. They can, under the right conditions, heat and disperse the gas that would otherwise collapse into new stars. The black hole, in a sense, regulates the star formation of its entire host galaxy, acting as a thermostat that prevents runaway growth. When the gas supply is exhausted, or when the feedback has heated the surrounding medium sufficiently, the black hole quiets down. It becomes quiescent, like Sagittarius A star today, an enormous but relatively dormant presence at the galaxy's heart. Star formation in the galaxy slows and eventually halts. The galaxy transitions from a vigorous, gas-rich, star-forming system into a quieter, older, more sedate collection of aging stars. The timing of this process, the balance between black hole growth and galaxy growth, between feedback and star formation, is one of the central questions in modern observational cosmology. Large surveys of the distant universe have traced how both galaxies and the quasars that mark actively feeding black holes have evolved over cosmic time. Both were far more common and more luminous in the early universe, when gas was abundant and the universe was dense and chaotic. Both have become quieter as the universe has aged and expanded, and the gas supply has thinned. And when galaxies collide, as they do regularly on cosmological timescales, their central black holes will eventually merge. As two galaxies fall together and their stars and gas interact and intermingle, the supermassive black holes at their respective centers gradually spiral inward. They form a binary system, two enormous black holes orbiting each other at ever-decreasing distances. As their orbit tightens, they radiate gravitational waves, ripples in the fabric of space-time that carry away the orbital energy. Eventually, after an immense span of time, the two black holes merge, releasing an extraordinary burst of gravitational radiation. This process is, right now, being traced by pulsar timing arrays, networks of extremely precisely timed neutron stars distributed across the galaxy. The gravitational waves from merging supermassive black holes across the observable universe are expected to produce a background hum of space-time ripples, and recent data from multiple pulsar timing collaborations have suggested, tantalizingly, that precisely such a background may already be detectable. The direct detection of gravitational waves from stellar mass black hole mergers, of course, was already achieved spectacularly in 2015, when the LIGO Gravitational Wave Observatory recorded the signal of two black holes, each roughly 30 solar masses, merging 1.3 billion light-years away. The signal lasted a fraction of a second. The peak power output exceeded that of every star in the observable universe combined. It was the loudest event ever recorded by human instruments, and it arrived as a gentle vibration far smaller than the diameter of an atomic nucleus. Inside the horizon, what theory tells us, no human instrument has ever observed anything from inside a black hole's event horizon. No human instrument ever can. What happens inside the horizon is, in the most absolute sense possible, forever beyond our direct observational reach. And yet, physics is not silent on the question. General relativity, applied with mathematical faithfulness to the interior of a black hole, makes predictions that are deeply strange and deeply challenging to intuition. Once inside the event horizon, the roles of space and time appear to interchange. Beyond the horizon, the singularity lies not in a spatial direction, not over there in the sense of being at a particular place, but in the future. It is not a location, but a moment in time. And just as no one, inside or outside a black hole, can travel backward in time, no one inside the horizon can avoid the singularity. It is simply where time ends. The singularity itself is a wound in space-time. General relativity's field equations, which describe the curvature of space-time in response to the distribution of matter and energy, produce values of infinite curvature at the singularity. In the language of mathematics, this is called a geodesic incompleteness. There are paths through space-time that simply stop. They do not continue. They reach an end. Most physicists believe this is not a true description of physical reality, but rather a signal that general relativity is incomplete. Just as Newtonian mechanics gave way to relativity when pushed to extreme regimes, so too may general relativity give way to a more complete theory when space-time curvature reaches extreme values. A theory of quantum gravity, reconciling the curved space-time of general relativity with the discrete, probabilistic, and fundamentally uncertain world of quantum mechanics, would presumably resolve the singularity into something finite and physically meaningful. What that something might be is the subject of active research. String theory, one of the leading candidates for a theory of quantum gravity, suggests that the fundamental constituents of nature are not point-like particles, but tiny, one-dimensional strings of energy, and that space-time itself may be a higher dimensional structure in which our familiar four dimensions are embedded. In this framework, the singularity might be replaced by a region of extraordinary but finite density, where stringy effects become dominant. Loop quantum gravity, another approach, quantizes space-time itself, treating it not as a smooth continuum, but as a discrete network of tiny loops. In this picture, the singularity might be replaced by a quantum bounce, a moment at which matter reaches extreme but finite density, and then rebounds outward. a scenario with deep connections to the cyclic universe models described by the Big Bounce theory. The inside of a black hole, inaccessible to observation, and perhaps even to the full power of current theoretical physics, represents the ultimate limit of our knowledge. It is the place where our best theories fail us. It is, perhaps, the most productive frontier in all of science, the deep future, black holes, and the end of everything. We have spoken of black holes in the present and the near future, their formation, their properties, their role in shaping galaxies. But to understand their full significance, we must travel much further. We must follow the universe all the way to its final chapters. 10 billion years from now, our galaxy and the Andromeda Galaxy will complete their gravitational waltz and merge. The collision will not destroy either galaxy's stars. The distances between individual stars are so vast that actual stellar collisions would be rare, but the shapes of both galaxies will be transformed utterly. Gas clouds will collide and trigger enormous bursts of star formation. The two central black holes, Sagittarius A star and Andromeda's own supermassive black hole, both carrying masses of millions of solar masses, will spiral toward each other and eventually merge in a cataclysmic release of gravitational radiation. The resulting galaxy, sometimes called Milkomeda by cosmologists with a taste for portmanteau, will be an enormous elliptical structure, rich in old stars, poor in remaining gas, over the next tens to hundreds of billions of years. The expansion of the universe will continue to accelerate under the influence of dark energy. The galaxies of the local group, the Milky Way, Andromeda, and their smaller companions, will eventually form a gravitationally bound island in an expanding sea. All other galaxy clusters, all other superclusters, will recede beyond the cosmological event horizon, invisible and forever out of reach. Then the stars will begin to die. The most massive stars, the brilliant blue giants, will burn through their fuel in millions of years. The sun-like stars will exhaust themselves in billions to tens of billions of years. The red dwarfs, the smallest, faintest, most miserly of stars, will continue to burn for trillions of years, but even they cannot last forever. By approximately 100 trillion years from now, the last stars will fade. White dwarfs will cool and dim over incomprehensibly long timescales. Neutron stars will cool. Brown dwarfs, objects too small to ever ignite nuclear fusion, will roam the darkness. The universe will be a cold, dark, diffuse collection of stellar remnants, separated by vast and growing distances, bathed only in the faint and ever-cooling afterglow of radiation. And in the centers of what were once galaxies, the supermassive black holes will endure. Having consumed enormous quantities of matter during the active era, and having grown through mergers, these colossal objects will persist long after every star has gone dark. They will be the last major structures in a cooling cosmos. But even they are not permanent. Hawking radiation, that slow quantum leak, will continue to drain them. For the most massive, supermassive black holes, the timescale is extraordinary, on the order of 10 to the power of 90 years, and for the very largest, perhaps 10 to the power of 100 years or more. These are numbers so vast that they dwarf the current age of the universe by incomprehensibly large factors, but they are not infinite. One by one, over timescales that render the current age of the universe a rounding error, the black holes will evaporate, each one ending in a final burst of Hawking radiation, each one releasing in that last flash the accumulated energy of billions of years of cosmic history. each one winking out and leaving behind, if Hawking's original calculation is even approximately correct, nothing but a fading glow of thermal radiation dispersing into an ever colder void. After all, the black holes are gone. What remains is almost beyond conception. A universe of extraordinary age, extraordinary emptiness, and extraordinary coldness. Individual protons and neutrons, if they are stable on these timescales, and there is theoretical reason to believe that protons, too, may eventually decay, will drift through an essentially empty cosmos. Electrons and positrons will roam the void, separated by distances larger than our current observable universe. Photons, utterly free, will travel in straight lines through a universe growing steadily more diffuse. The temperature everywhere will approach, though never quite reach, absolute zero. This is what physicists sometimes call the heat death of the universe. Not death by fire, but death by cold, by exhaustion, by the slow, inexorable increase of entropy that the second law of thermodynamics demands, a state of maximum disorder that offers no further gradient, no further distinction, no reservoir of energy that could power any process, however simple. A universe of perfect, featureless, eternal cold. The questions that remain, and yet, even here, at the absolute limit of our theoretical vision, even at the heat death of everything we know, physics is not silent. Quantum mechanics tells us that even perfect emptiness is never truly empty. Even the most diffuse and cold vacuum is host to quantum fluctuations. And quantum fluctuations, given truly unlimited time, can produce truly extraordinary things. In a universe of sufficient age, and by the timescales we have been contemplating, our current cosmic age is a fleeting instant. Quantum fluctuations might randomly reassemble particles into configurations of arbitrarily low probability. This is not a practical expectation. The timescales for truly significant quantum reassembly dwarf even the evaporation times of supermassive black holes by factors that cannot be meaningfully expressed in ordinary language. But in a universe of infinite duration, every finite probability event, no matter how vanishingly small its probability, eventually occurs. Could a quantum fluctuation, in a universe of near infinite age, spontaneously produce a new inflating bubble of spacetime? Could the structure of space itself be fundamentally unstable, with our universe existing in a metastable state that could at any moment and without warning transition to a true ground state through the bubble mechanism we discussed earlier? Could the cyclic models of cosmology be correct, and the extreme density of the final stages of a contracting universe, if contraction is indeed what awaits us, produce the conditions for another Big Bang, another cycle, another age of stars and galaxies and perhaps consciousness? We do not know. We cannot know, not with the tools currently available to us. These questions sit at the intersection of the very large and the very small, at the boundary between what has been observed and what has only been theorized, at the edge of what human minds can currently conceive. But this is precisely where science lives at its most alive, not in the settled territories of established knowledge, but at the frontier, at the place where the questions become harder and more beautiful, where the answers become more elusive and more consequential. Every civilization that has looked up into the night sky has known that the darkness between the stars is not empty. They felt, even without the mathematics to articulate it, that the darkness had structure, that it had history, that it had, in some sense we could not yet name, something to teach us. We have come a long way since then. We have measured the curvature of space-time. We have recorded the gravitational waves from colliding black holes. We have photographed the shadow of a singularity across 50 million light-years of space. We have traced the history of the universe back to fractions of a second after its birth and forward to the near extinction of all matter. And still, the deepest questions remain. What happens inside the horizon? Is information truly preserved? What was there before the beginning? Does the universe have a cycle, a breath, a pulse that extends beyond what we can observe? The black hole holds all of these questions in its gravity, pulling them together, refusing to let them disperse into the cold and comfortable certainty of the known. It is not, in the end, simply a cosmic object. It is a question. The darkest, densest, most inescapable question the universe has managed to ask of the creatures it produced. And we are still, with all our telescopes and equations and audacious imagination, still only beginning to listen for the answer. The perspective of deep time. Since the first human beings looked up at the night sky and wondered, we have been asking the same fundamental question from 1,000 different angles. What is all of this? How did it come to be? What does it mean? The discovery of black holes and the gradual unfolding of their extraordinary properties across more than a century of theoretical and observational science has given those ancient questions a new and sharper focus. It has shown us that the universe is not merely large and old, but strange beyond our most creative initial expectations, that the rules governing it permit structures and behaviors that no pre-scientific imagination, however fertile, could have conjured. It has shown us that the cosmos contains within itself a built-in humility principle. Just as the cosmological horizons we discussed limit what we can see, the event horizon of a black hole places an absolute limit on what can be known from outside. Some truths about the universe are, by the laws of physics themselves, hidden from any external observer forever. This is not a temporary limitation of technology or cleverness. It is woven into the structure of space-time. And yet, paradoxically, this recognition of limits has proved enormously productive. The information paradox has driven decades of fundamental theoretical work. The search to understand what happens at the singularity has pushed physicists toward quantum gravity and string theory and loop quantum cosmology. The correlation between black hole mass and galaxy properties has revealed an intimate cosmic connection that is reshaping our understanding of how structure formed in the universe. The black hole, in other words, is not merely an object of study. It is a tool of discovery. The universe has placed these extraordinary objects at the boundaries of the knowable, and in our efforts to understand them, we have learned things about space-time and quantum mechanics and information and entropy that would never have emerged from studying more comfortable and accessible phenomena. We are living in a remarkable moment. The first images of event horizons have been obtained within living memory. Gravitational wave astronomy is in its infancy, its potential barely touched. Space-based gravitational wave detectors are being planned that will extend sensitivity to the mergers of supermassive black holes across the observable universe. The James Webb Space Telescope is probing the first billion years of cosmic history, searching for the progenitors of the supermassive black holes we find fully formed in the early universe, trying to solve the mystery of their implausibly rapid growth. In the years and decades to come, we will see more. We will measure the properties of event horizons with greater precision. We will watch more black holes merge through the medium of gravitational waves. we will, perhaps, begin to place meaningful constraints on what happens just beyond the threshold of the unknown. And generation after generation of scientists and curious minds will stand at the edge of what is knowable and peer into the darkness, the way human beings have always stood at the edges of continents and oceans and asked what lies beyond, knowing that the question itself, the asking, the reaching, is as important as any particular answer. The universe began, as best we can tell, in a singularity, a point of infinite density, a wound in space-time from which everything we know, everything we are, everything we have ever wondered about, emerged in an instant of expansion and cooling and gradual, beautiful complexity. And in the black holes distributed across the cosmos, in the singularities that form at the endpoints of stellar life, we see an echo of that beginning, a reminder that at the most extreme limits of what physics can describe, something profound awaits. Not an ending, not a void, but a question so deep and so fundamental that the universe itself does not yet have a language for the answer. We are made of the remnants of dead stars. We carry, in the iron in our blood, the legacy of supernova explosions that preceded our sun's birth by billions of years. We are the universe's way of knowing itself. And black holes, dark, extreme, paradoxical, humbling, are, perhaps, the universe's way of reminding us how much there is still left to know. All that remains is to keep asking. The tools we use to listen to darkness. For most of human history, astronomy was a pursuit of light, visible light, gathered by eyes and eventually by mirrors and lenses of increasing size and sophistication. The universe revealed itself through photons, and since black holes, by definition, emit no light of their own, they were for centuries purely theoretical, mathematical consequences of equations, not objects that could be pointed to in the sky. The 20th century changed this, initially through indirect means. The first compelling observational evidence for black holes came not from any emitted radiation, but from the behavior of objects around them. Stars orbiting the centers of galaxies too quickly for any other explanation. Gas in binary star systems heated to temperatures only achievable by material falling into extraordinary gravitational wells. X-ray sources whose variability was too rapid to be explained by anything other than an extremely compact central object. But in the 21st century, we have graduated to direct observation. Two entirely new windows on the universe have opened, each transforming our ability to study black holes from theory to observational reality. The first is X-ray astronomy, which from space-based observatories has revealed the universe's most energetic phenomena with extraordinary clarity. Missions including ROSAT, Chandra, XMM Newton, and now more advanced successors have mapped the X-ray sky with ever-increasing precision, tracing accretion disks, jets, and the superheated coronae that surrounds actively feeding black holes. The spectrum of X-rays from an accretion disk carries encoded within it information about the geometry of space-time in the immediate vicinity of the event horizon. Information that, when carefully analyzed, allows physicists to measure properties of black holes, including their spin. The iron K-alpha spectral line has proven particularly valuable. Iron atoms in the innermost regions of an accretion disk, heated and ionized by the intense radiation environment, emit X-rays at a characteristic energy. But because some of this emission comes from regions of extreme space-time curvature, close to the event horizon of a spinning black hole, relativistic effects broaden and distort the line in characteristic ways. By measuring the precise shape of this distortion, astronomers can probe conditions within a few gravitational radii of the event horizon itself. It is the closest thing we have, from X-ray observations alone to peering at the boundary of the black hole. The second revolutionary window is gravitational wave astronomy, barely a decade old as a practical observational discipline, but already transforming the field. Gravitational waves are not light. They are not electromagnetic radiation of any kind. They are, rather, oscillations in the fabric of space-time itself, distortions that propagate outward from accelerating massive objects at the speed of light, squeezing and stretching the distances between everything they pass through. When two black holes spiral together and merge, they produce gravitational waves of extraordinary intensity during the final moments before coalescence. The LIGO and Virgo detectors that first registered these signals are instruments of almost impossible delicacy. They measure changes in the lengths of 4-kilometer arms to a precision smaller than 1/10,000th of the diameter of a proton. To put this in context, this is roughly equivalent to measuring the distance to the nearest star, about 4 light years, to a precision of less than a human hair. The engineering required to isolate these instruments from every source of vibration, from traffic on distant roads to waves breaking on shorelines hundreds of kilometers away, from the quantum noise inherent in the laser light itself, represents one of the most ambitious technological achievements in the history of science. And the signals, when they arrive, are simultaneously brief and rich with information. A chirp, typically lasting a fraction of a second to a few seconds, sweeping upward in frequency as the two black holes spiral together faster and faster, followed by a brief, complex ring-down as the merged remnant oscillates and settles. From this signal, carefully matched against the predictions of numerical relativity simulations, physicists can extract the masses and spins of both initial black holes and the final merged product, the distance to the merger, and even information about the orientation of the orbital plane. The catalog of gravitational wave events has grown rapidly. Dozens of confirmed detections have been made in just a few years of observation. Black hole mergers involving masses ranging from a few solar masses to over 100. A handful of neutron star mergers, which also produce electromagnetic signals, allowing for a revolutionary multi-messenger view of the most extreme collisions in the universe. Each event is a laboratory for general relativity, testing Einstein's equations in regimes of extreme space-time curvature that no terrestrial experiment could ever approach. And this is just the beginning. Next-generation ground-based detectors with arm lengths of tens of kilometers will increase sensitivity by orders of magnitude, detecting black hole mergers across much larger fractions of the observable universe. The planned space-based LISA mission, a gravitational wave observatory with arm lengths of millions of kilometers operating in the quiet environment of interplanetary space, will be sensitive to the low-frequency gravitational waves produced by supermassive black hole mergers across the entire visible universe. Every time two massive galaxies merge anywhere in the cosmos, their central black holes will eventually collide, and LISA will hear it. A merger perhaps billions of years in the making, announced in a gravitational chorus that our instruments will be able to decode. And beyond these two windows, a third may be opening. Neutrino observatories, detectors capable of registering the extremely rare interactions of these near-massless, nearly undetectable particles, are growing in size and sensitivity. The ice cube detector at the South Pole, a cubic kilometer of Antarctic ice instrumented with thousands of sensors, has already detected high-energy neutrinos from extragalactic sources, including what appears to be a contribution from active galactic nuclei powered by supermassive black holes. As these detectors grow larger and more sophisticated, they will add yet another messenger, another channel of information about the most extreme environments in the universe. We are, in a very real sense, giving ourselves new senses. For most of human history, we observed the cosmos through a single channel, visible light. We are now building the instruments to hear its gravitational voice, taste its neutrino breath, and feel the warmth of its most energetic X-ray and gamma-ray outbursts. Black holes, which are invisible to conventional telescopes, become loud and distinctive in these new channels. The universe has been sending us messages in frequencies we could not previously detect. We are only now beginning to learn how to receive them. The story of black holes is, in this sense, not just a story about exotic astrophysics. It is a story about the expansion of human perception, about our species' determination to see what cannot be seen with unaided eyes, to hear what falls outside the range of human hearing, to understand what lies beyond the reach of ordinary experience. Every new detector we build, every new signal we record, every new piece of information we wring from the darkness is an act of reaching. Black holes sit at the edge of the knowable. They always have, and they likely always will. There will always be more to learn, more to discover, more puzzles generated by each answer we find. But the edge has moved. It moves every time a new gravitational wave chirp is recorded. Every new X-ray spectrum is analyzed. Every new image of a glowing ring of plasma around a shadow in the sky is processed and studied. And as long as human curiosity endures, as long as we keep building instruments and asking questions and pointing our new senses at the darkness, the edge will keep moving. The universe is patient. The darkness is deep. And we are only just beginning. The mirror. We didn't expect. There is a final thing worth saying about black holes, something that goes beyond the mathematics and the observations and the paradoxes. When physicists began to seriously study black holes in the middle of the 20th century, they were, on one level, simply following the logic of Einstein's equations to their conclusions. The equations demanded that such objects exist under the right conditions. The physicists followed the math, the way scientists always follow the math when it leads somewhere interesting, even, especially, when it leads somewhere strange. But over the decades, black holes became something more than a consequence of general relativity. They became a mirror in which the rest of physics saw its own reflection and often found it incomplete. The information paradox is the most obvious example. A question about what happens to the information content of matter consumed by a black hole turned into a decades-long confrontation between quantum mechanics and general relativity, exposing in sharp relief the deep incompatibility between our two best theories of nature. The paradox has not yet been fully resolved, but the attempts to resolve it have produced extraordinary insights into the holographic principle, the startling suggestion, now taken seriously by a significant fraction of theoretical physicists, that the information content of a volume of space-time may be encoded on its boundary surface, much as a three-dimensional hologram is encoded in a two-dimensional film. If the holographic principle is correct, it has consequences that reach far beyond black holes. It suggests that the three-dimensional world we experience might, in a fundamental sense, be a kind of projection, that the deepest description of reality is not the rich, volumetric space-time we navigate every day, but something lower dimensional encoded on a distant surface. This idea, developed most fully in the anti-de Sitter/conformal field theory correspondence, first articulated in the late 1990s, has transformed large parts of theoretical physics, providing new computational tools and new conceptual frameworks that have found applications in condensed matter physics, quantum information theory, and cosmology, all from asking what happens to information inside a black hole. Black holes have also forced physicists to think more carefully about entropy and thermodynamics. In the early 1970s, it was proposed that a black hole carries entropy proportional to the area of its event horizon. This was a radical suggestion. Entropy, in classical thermodynamics, is a property of the internal states of a system. How could a black hole, which has no internal structure visible from outside, carry entropy at all? And why would it scale with area rather than volume? Hawking's discovery that black holes radiate gave this proposal physical grounding. If a black hole has temperature, it must have entropy. Thermodynamics demands it. The resulting framework, black hole thermodynamics, establishes deep formal parallels between the laws governing black hole mechanics and the laws of classical thermodynamics. These parallels are now understood to be more than analogies. They reflect genuine physical identities. Black holes obey thermodynamics, and in doing so, they have pointed toward the extraordinary idea that thermodynamics itself, entropy, temperature, the arrow of time, might be emergent properties of space-time, consequences of a deeper quantum gravitational structure we have not yet fully mapped. Every major discovery in the study of black holes has revealed that the universe is stranger, richer, and more fundamentally surprising than the preceding generation of scientists had supposed. The discovery that they radiate. The discovery that they carry thermodynamic entropy. The discovery that they shape the galaxies around them. The first images of their event horizons. The first sounds of their mergers transmitted to us through gravitational waves across 1 billion light-years of space. The pattern is consistent. Black holes are not merely extreme versions of ordinary astrophysical objects. They are windows into the fundamental architecture of reality itself. They are places where the universe's deepest structures, the relationship between space-time and quantum mechanics, between gravity and thermodynamics, between information and entropy, are exposed with a clarity impossible in any gentler environment. We are fortunate to live in an era when these windows are opening, when instruments are finally sensitive enough and clever enough to hear the whispers that black holes send across the cosmos, when the mathematics is mature enough to pose the right questions, even when the answers remain obstinately elusive. Black holes are not the end of the story. They are, in a very real sense, where the story gets interesting, where the universe looks back at us through the darkness and quietly asks us what we think we know.